Good morning, everyone, and welcome to today's lecture. This is heat transfer lecture number 5 on radiation, and in today's class, we hope to finish this topic once and for all. So I hope you remember what we had done in the previous classes. Now, since there is no mic and you cannot speak, it's my humble duty to let you know what we had done in the previous class, and if I am correct, if my memory serves me correct, which never does, we were dealing with Stephen's law in the previous class. Yes or no? Do we remember Stephen's law? Only one student remembers Stephen's law. That is not a good sign. Okay. So what does Stephen's law says? It says that for any body, the emissive power will be equal to E sigma T raised to the power 4, where E stands for the emissivity, sigma stands for the Stephen's constant, and T stands for the absolute temperature. This is the emissive power. If I talk about how much energy it is radiations it is emitting, that will be equal to E A sigma T raised to the power 4 multiplied by the time delta T. Then I have some raised hands from everyone that we understand this, we remember this. Then we had understood what is the rate at which this energy is gained or lost. Remember, when I talk about this equation, the equation in yellow, I'm only talking about the energy it is radiating or emitting. But Prevost theory of exchange tells us that at the same time it is also receiving energy which is emitted by a nearby body. If I take that point into calculation, my E, the net energy that it is emitting, will become E sigma T raised to the power 4 minus T naught raised to the power 4. Here I have assumed that T, the temperature of the body, is greater than T naught, and T naught is the surrounding temperature. If I convert this into the rate of loss of heat, delta Q by delta T, it becomes E sigma A T raised to the power 4 minus T naught raised to the power 4. Yes or no? Do we remember this equation? The equation in pink. This is the rate at which energy is gained or energy is lost when a body is at an absolute temperature capital T and the surrounding is at a temperature T naught. From here I can derive the relation at which the temperature of the body changes. I can call it as delta theta by delta T, the rate of cooling, you call it, the rate at which the temperature of the body is coming down, and it is equal to E sigma A divided by M standing for the mass of the body, S standing for the specific heat capacity, T raised to the power 4 minus T naught raised to the power 4, and this equation is the equation in blue. This equation in blue gives us the rate at which the temperature of the body goes down. Do we remember this? Can I have some raised hand that we remember this? Everybody can see this on your screens, yes or no? It's very difficult for me to see your signs because they are getting lost. Everyone understands this? Everyone remembers this? Thumbs up? Thumbs up or no thumbs up? Okay. Now just to continue, so that as I understand that this is a very important topic, this Stephen's law, and I have seen a lot of questions coming on this Stephen's law. Just to get back, just solving a question, one or two question on Stephen's law is the need of the hour, and that is why this question comes up to you. And I would need answers for this question. I hope you can read this question. The question goes like this, very simple. Temperature of a piece of metal is increased from 27 degrees Celsius to 327 degrees Celsius. The rate of emission of radiation by this metal will become how many times? And what is the answer for this one? A, B, C, D, double 4, 8, 16. What is the answer? The answer is the initial temperature is 27 degree Kelvin, 27 degrees Celsius. So this becomes 300 Kelvin. Yes or no? The initial temperature is 300 Kelvin. The final temperature is 600 Kelvin. The temperature becomes 2 times. If the temperature becomes 2 times, it is 2 raised to the power 4. So the rate of the emission will become 16 times. Do we understand this? Since there is no mic, you will have to raise hand so that I understand that you understand. Okay, again, as you can see, the number of questions on this particular topic, rate of heat of cooling, is very large. I'll give you one more question. This one. 4 bodies of specific heat, S1, S2, S3, and S4 are cooled in the same surrounding. If S1 is greater than S2 is greater than S3 is greater than S4 and the temperature of all the 4 bodies is the same, then the specific heat of the body which cools the fastest, which is the body that is going to cool the fastest is, and I'm waiting for your answers. 19. Which body will cool down the fastest? This is how questions are framed. And you should be able to give me an answer for this. A, B, C, D, 1, 2, 3, 4. And the answer is, as I told you just now, I revised it, that the rate of heat, rate of cooling or rate of increase of temperature is inversely proportional to specific heat. The body which has more specific heat will take less time. The body with less specific heat will take more time. So which one will cool fastest? The body with more specific heat, or the body with the least specific heat? The body with the least specific heat will cool down the fastest. Yes or no? Delta theta by delta T is inversely proportional to specific heat. That means the time it takes is directly proportional to S. This thing was given in your sheet. Yes or no? I had marked it in your sheet. The answer is 4. Do we understand this? Can I have some raise hand that we understand this? Okay. One more comes your way, which is this one. I hope you all can see this. A solid sphere of radius r and a hollow sphere of internal radius small r and external radius r are made up of copper. These are heated to the same temperature and then allowed to cool in the same surrounding. Which one will cool? 4 options are given. A, B, C, D, 1, 2, 3, 4. I already discussed this with you. Let's see. A solid sphere. 1, 2, 3, 4. Which one? Hollow sphere will cool first. I'm getting this answer. I'm also getting answer where both will cool at the same rate. So the answer has to be one of these. Which one? Obviously, solid sphere is cut out. Only solid sphere will cool. This is cut off. The only two options are B and C. Which one is the correct one? Both will cool at the same rate or not? Or hollow sphere will cool first. Remember, it's not a completely hollow sphere. It is a sphere which has got a spherical hole. Now remember, rate of cooling is proportional to E. E is same for all, both the spheres. Sigma, same for everyone. Area, the outer area is same. Temperatures are same. It is inversely proportional to M. Masses are same here. It is inversely proportional to specific heat. That is also same. So both will cool down at the same temperature. Do we understand this? So both will cool down at the same rate. So the answer would be option number B goes away. The answer would be option number C. Do we understand this? Can I have some raise hand that we understand this? So basically, what I mean to say by all this is, if we just remember these four formulas, which I had just given you at the beginning of the class, it is more than enough for us to solve any question that can come. I'm just looking for one specific question. So let me have a look at that. If I get this question, we will solve it, and then we would move away. And that is one question that I was looking for. I have got this, and I hope that you can give me the answer to this one. This is the question that comes up. A black body at a temperature of 227 degrees Celsius radiates heat at the rate of 7 calories per centimeter square per second. At a temperature of 727 degrees Celsius, what would be the rate of cooling in the same units? Can I have your answers, please? Question number 34 from your sheet. Can I have the answers, please? I'll wait for a minute. Do I have the answers, my dear friend? So, shall I help you out? Okay, so basically how you got to do this question? The initial temperature is 227 degrees Celsius. Yes or no? I will convert that into Kelvin. So how much it is in Kelvin? 227 plus 273. It will be 500 Kelvin. Yes or no? Initial temperature is 500 Kelvin. Final temperature is 1000 Kelvin. The temperature has become twice. The temperature has become twice. Temperature has become twice. Emissive power is directly proportional to T raised to the power 4. Temperature has become twice, so emissive power will become 16 times. Emissive power will become 16 times. The initial emissive power is 7. The final emissive power will be 7 multiplied by 16. And the answer would be 7 multiplied by 16, and the answer would be 112. These are the type of questions that you can expect in the examination hall. Do we understand this? Okay. Well, let us move on and finish the rest of the theory for this chapter. And the next thing that we are going to study is, again, a lot of questions come on this particular topic. The next thing that we are going to study is known as this. And what is this? This is Newton's law of cooling. Now, what does this Newton law of cooling state? Have you heard about this Newton law of cooling? Yes or no? Yes, Newton law of cooling. And it simply tells us about the rate of cooling. When I say rate of cooling, it means the rate at which the temperature of the body is coming down. Rate of heating means the rate at which the temperature of the body is going up. It is rate of cooling, but it is also applicable for rate of heating. Normally, we assume that things are at a higher temperature than the surroundings. Therefore, it is known as rate of cooling. With the rate of cooling or rate of heating doesn't matter. It is the one and the same thing. Do we understand this? So, Newton laws of cooling simply states what it says. You are going to write this, whatever I mark it. The rate of cooling d theta by dt is directly proportional to the excess of the temperature of the body over the surroundings. Do we understand this? The rate at which the body cools is directly proportional to how much is the excess of its temperature. Now, this temperature that we are talking about, it can be in degrees Celsius, it can be in Kelvin, because it is the difference in temperature. And if it is difference in temperature, the difference in temperature on the Celsius scale and the difference in temperature on the Kelvin scale, they both are same. So basically, Newton's law of cooling states that the rate at which the body cools down, d theta by dt, I hope everyone is writing this, d theta by dt is directly proportional to theta, which is the temperature of the body, minus theta naught, which is the temperature of the surrounding. Both of these temperatures can be in Celsius, they can also be in Kelvin. Theta is the temperature of the body. Theta naught is the temperature of the surroundings. Theta minus theta naught is the excess of temperature. I'll give you a minute to note this down. Anyone has any doubts on this? I guess not. So please note it down. I'll give you a minute. Have you noted it down, bacha? Okay. Then let us move ahead and move to this. In the previous slide, what we had seen that the rate of cooling delta theta by delta T is proportional to theta minus theta naught. So if I remove that proportionality sign, I will have a constant K, and this is the constant K. I hope all of you can see this constant. A negative sign is also included with this constant. Why is this negative sign included? Because as the body cools down, as the body cools down, the rate of cooling is going to decrease, and that is why this negative sign is incorporated. So I've incorporated a negative sign and a constant multiplied by the excess of temperature. Do we understand this? Can I have some raised hands that we understand this? Now, what is the value of this constant? And you may not be asked this value because its derivation is out of your syllabus. But if you want to know what is the value of this constant, the value of this constant, and I'm writing it in bold, is 4 times E. 4 is a number, E is the emissivity, into sigma. Sigma is your Stephen's constant, into area of the body, into the temperature of surrounding, theta naught raised to the power of 3. Remember this, raised to the power of 3 divided by mass of the body into the specific heat of the body. This is the value of this constant K. If a very tough question comes, and probably that question will come in JEE or JEE Advanced, maybe, then they might ask you the value of this constant. But if you can remember this value and it's a very tough question comes, I'm sure you will be the only one knowing that this is the value of the constant and you would be able to solve this question. I'll give you 2 minutes to write everything that I have marked down. I hope you do not miss on anything. Have we noted it down, bacha? Everyone? Okay. Now the formula that we saw is the actual formula. That is also not the actual formula. The actual rate of heating or the actual rate of cooling, we have already seen that formula. Do you remember that formula? The actual rate of heating and actual rate of cooling. Does anyone remember that formula for actual rate of cooling or the actual rate of heating? At the beginning of the class, I had already told you that the formula for actual rate of heating or actual rate of cooling is given by this. Oops, something wrong. Let me again do it. I've probably done a wrong screen share. This so we shared. Oops, not this. I guess my brain is not working correctly today. I would now share it. Okay, we'd actually seen that the rate of heating or the rate of cooling is given by this formula. Do we remember this? Yes or no? But right now at this point in time, when I am changing my statement, and I'm changing my statement to here, rate of cooling d theta by dt, or I can call it as delta theta by delta t, whatever. Right now, I am telling you that this is equal to minus k times theta minus theta naught. Or if I just write theta as t, it will be t minus t naught. Now you must say, sir, how can one rate of cooling have two different formulae? No, they are not two different formulas, bacha. These two formulas are exactly same. Not exactly same. The niche wala formula, when I say niche wala formula, I mean the green wala formula. The green wala formula is derived from the blue wala formula. So this blue wala formula actually gives you this green wala formula. This green wala formula does not come from heaven. It has been derived from the blue wala formula. The blue wala formula is the exact formula for rate of cooling or rate of heating. This formula is the exact formula. This formula is the exact formula. The green wala formula is only valid if the temperature difference is very small. This formula is only valid if theta minus theta naught is very small. This formula, the green wala formula, is only valid when the change in temperature, the difference in temperature between the body and the surrounding is very small. The actual formula is blue wala formula. Green wala formula is a shortcut type of formula which is only valid when the temperature difference is small. Do we understand this? Can I have some raise hand that we understand this? So Newton laws of cooling, if a question comes, please mark my words and write it. Newton laws of cooling, if the question comes, from where this Newton laws of cooling is derived. Remember, dear friends, this Newton laws of cooling is derived from the Stevens law, the original Stevens law. The blue formula comes from the Stevens law and the Prevost law. From that blue formula, green formula has been derived. Newton laws of cooling is derived from Stevens law. Do we understand this? Please remember this. This might come as a question. Please mark Stevens law in that answer. Now, I'm on the green formula, which is not an exact formula, which is a shortcut version of the blue formula. Now I'm going to the third formula, the third variation. And again, this third wala formula is derived from the green wala formula. So that is again a more distorted version of the actual formula. The third formula, which is being derived from the green wala formula, will come on your screens right away as soon as I start my magic, and the magic trick begins now. No, it does not begin. The baggage trick begins now. This is the third formula that is been derived from the green formula, which is again a more distorted version of the original formula. And in the distorted version, what has happened is that we are considering that the temperature, initial temperature is theta1 and the final temperature is theta2. Do we all see this? Initial temperature is theta1, final temperature is theta2. Temperature has fallen from theta1 to theta2 in time t. Do we all see this? Okay. Then this formula, which is derived from the green formula, the green formula is derived from the blue formula. This formula, the green formula, the actual law of cooling ka formula, is now converted into this. Theta1 minus theta2 divided by t will be equal to, instead of negative, we have a positive because we have not subtracted theta2 from theta1. We have not subtracted theta1 from theta2. We have subtracted theta2 from theta1. So instead of minus, it is plus now. Plus, we call this as the average temperature, which is known as the radiation correction. This is again a correction which is only valid if the temperature difference is very small. So I can use, instead of theta, I can use theta1 plus theta2 by 2, because the temperature of the body is continuously changing. Initially it was theta1, finally it is theta2. Which theta to take, you will ask. Then the sir will tell you, okay beta, do not take theta1, do not take theta2, take the average value, theta1 plus theta2 by 2. So instead of theta, I have written theta1 plus theta2 by 2 minus theta naught. Do we understand what has been replaced by what? Yes or no? And this is the formula, my dear friends, which we are going to use in all the calculations, in all the questions that are going to come in the exam on Newton's law of cooling, NLC, Newton's laws of cooling. This is the third variation of the actual formula. The actual formula is the green formula, is the blue formula. Green formula is derived from the blue formula, and this third one is again a distorted version of the green and the blue formula. Do we understand this? Do we understand this? Three formulas I have given you, beta. The original formula is blue, green is the distorted version. The third one, what color should I give it to? Let me call it pink formula. This is the pink formula. The pink formula, pink formula, pink formula. Why it is coming blue? Why it is coming yellow? The pink formula, pink, 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 pink is my favorite color. Pink, pink, pink. The pink formula, aha, nice color. The pink formula is the third formula, which is the distorted version of the green or more distorted version of the blue formula. And this is the pink formula that we are going to use in all the questions on Newton's laws of cooling. Have you noted down this pink formula? I'll give you a minute. Okay, you noted it down. Since you have noted it down, what we'll be doing is writing the limitations of this Newton's law, and these are the most important limitations. A question will come directly on those. You will have to note them down in the copy that you have made. Strict limitations of Newton's law, and the first limitation is very simple, that temperature difference should not exceed 35 degrees Celsius. Otherwise, my dear friends, otherwise, theta minus theta naught, otherwise, the green formula is not valid. We'll have to move to the blue formula. Do we understand this? The green formula is only valid when the difference in temperature is less than 35 degrees Celsius. The heat is lost only by radiation, so we are neglecting the other formats, mainly convection and conduction. This law is an extended form of Stephen's law. It is derived from Stephen's law. Will you remember this? Can I have some raise hand that we understand this, that we remember this, sir? I'll give you a minute to note down these limitations. Have you noted down the formula, beta, and the limitations? Okay. Since we have noted down the formula and the limitation, now is our humble duty to utilize this formula. And how are we going to utilize this formula? How are questions framed? This is a question that is coming on your screens right now, and I hope that you can see it all. Think you can see it all, and that is how questions are framed. And I'll give you a minute to think about it. A body takes 4 minutes to cool from 100 to 70. The room temperature is 15. Then how many minutes it will take to cool from 70 to 40? 100 to 70 is cooling down in 4 minutes. How much time will it take to cool from 70 to 40? That is the question. Since this is the first time you are trying this, I'll give you 2 minutes. Think about the question. You already know how to solve it. I'll be very happy if you can do it on your own. I'll give you a minute, 2 minutes, 3 minutes. Think about it and give me the answer. Your time starts now. Well, have you tried the question? Anyone got any answer? No? Well, not good? Let us try to solve the question. So what are the information given in the question? The information given in the question are straight away. The surrounding temperature is 15 degrees Celsius. Do we understand this? From 100 to 70, it cools in 4 minutes. Do we understand this information from the question? We have to find the time it takes to cool from 70 to 40. Yes or no? How to do it? How to do it? How to do it? How to do it? Nothing. Let us go on to this stage first. I will apply the formula theta1 minus theta2 divided by t is equal to k into theta minus theta naught. And we must remember that the value of this theta is theta1 plus theta2 divided by 2. Do we understand what I am doing here? Just put the values and see what I get. The value of theta1, the green one, is 100. The value of theta2, the pink one, is 70. So theta1 minus theta2 becomes 100 minus 70. The value of time is 4. Do we see this? So I divide it by 4. That must be equal to k. I don't know what is k. K into theta. How do I get the value of theta? Value of theta will be theta1, is 100, plus 70. 100 plus 70 is 170. Divided by 2. 170 divided by 2. Do we understand this? Do we understand this? Minus 50. Minus 50. So what do I get from here? 30 divided by 4 is equal to k. 170 divided by 2 is how much? I think it is 85. Yes or no? Yes or no? It is 85 minus 85, na? 85 minus 15. How much is 85 minus 15? 30 by 4 is equal to k multiplied by 60. Yes or no? Do we understand what I am doing here? 30, 60 goes twice. From here I can find out the value of k, and the value of k would be 1 by 8. Yes or no? No or yes? Do we understand this? This was the red version, the version of the first thing. Now what do I go? What do I do? I go on to the blue version. For this condition, how much time it will take to go from 70 to 40? And how do I go about it? Again, I apply the same formula, theta1 minus theta2 divided by t should be equal to k times theta minus theta naught. Now I'll have to do the same steps over and over again. The only thing, the only difference is I know the value of k. The value of k is 1 by 8. Yes or no? We know the value of k. We know the value of k. The only unknown quantity is the value of t. I will give you time to solve it by yourselves, and I would be very happy if you can get me the value of t from the equation now. I'll give you a minute to show me your talent and hard work. Oh, it seems I have made a mistake. 85 minus 15 is not 60. It is 70. Yes, I stand corrected. Thanks for correcting me. So I will just remove this. I'll just remove this. So I'll just get onto the original thing. 30 minus 4 is 70k. From here, I can get the value of k. Thanks for correcting me. It was a genuine mistake. 3 divided by how much is 7 into 4? 28. 3 divided by 28. Thank you. Can you now give me the answer? So, how do I go about it? Very simple. I just put the values. Initial temperature is 70. 70 minus 40 divided by time, I don't know, so I just call it T. 70 minus 40 divided by T is equal to K. The value of K is 3 divided by 28 into the value of theta. How much is the value of theta? 70 plus 40 is 110, I think. 110 divided by 2 minus 15. Do we understand this? So let us see, how do I solve this? This is 30 divided by T is equal to 3 divided by 28. 110 divided by 2 is 55. 55 minus 15, I hope I'm correct this time, is 40. 1 0 and 1 0 go here, 3 and this go here. So I have the value of T, and the value of T is 28 divided by 4. The answer is 7. So the answer is 7 minutes. Do we understand this? Yes or no? No or yes? Now, this is I have solved step by step. Obviously, this is the right way. But again, you might not be having so much time in the examination hall to do it step by step. Then what do? Basically, what I have done on the right hand side in the red is to find out the value of k. You actually do not require to find out the value of k. Actually do not require to find out the value of k. You actually do not require to find out the value of k. What you can do is, you just can do some smart work. Let me call this as equation number 1. I hope everyone is looking here. Let me call this as equation number 1. Can everyone see this equation number 1? Yes, sir. No, sir. Better I go, sir. The yellow equation, sir, in the red box, sir. We all see this, sir. Let me call this equation as equation number 1, and let me call this equation again in the box. Again in the box. Painted green as equation number 2. As equation number 2. And here what do I do? Instead of writing the value of k, I cut the value of k and I simply write k. So what do I do is, in the red zone, I forget these 2 steps. I just go till this step. And then in the blue equation, I come till this step. In both these equations, I have k. I don't need to find out the value of k. I can divide 1 by 2 or I can divide 2 by 1. Do we understand this? Instead of finding out the value of K, we just divide equation number 1 by equation number 2. We just divide equation number 1 by equation number 2. What do I get if I do that? Remember, the way that I did it was absolutely correct. I just took a lot of time. I'm just trying to cut short everything. Do we understand this? So I'm now going to divide equation number 1 by equation number 2, and here I hope you can see this on your screen. I am dividing 1 divided by 2. I am dividing equation number 1 by equation number 2. So what do I have? On the left hand side, let me use a different color. Let me use black color. I have 30 divided by 4. This has to be divided by, this is 30 divided by 4, the black one. I hope you can all see this. 30 divided by 4 divided by 30 divided by t. This 30 divided by t is this one. Can we all understand this? Raise hands will give me more confidence that we understand this, sir. So 30 divided by 4 divided by 30 divided by t. Now I come to the right hand side. I have this k and this k will get cancelled. Do we understand this? So I don't have to worry about k. On the numerator, I will have 85 minus 15. And yes, my dear friend, it is 70 and not 60. It is 70 and not 60. It is 70 and not 60. On the right hand side, I have the right hand on the second equation. I have 55 minus 15. That is 40, my dear friends. That is 40, my dear friends. Straight away, I can cut this thing. I can cut this 30. Just a simple bit of calculation. And I will get my answer. A simple bit of calculation and I will get my answer as 7 minutes. I hope you understand this. Yes or no? No or yes? So on the left hand side, I have 1 by 4 divided by 1 by t. So t comes in the numerator, it becomes t by 4. On the right hand side, I have 7 by 4. So answer becomes 7 minutes. Do we understand this? How I have cut short 2 or 3 steps and I've divided straight away. You can now always do it by the original tarika. Takes one more step extra. But again, that one more step will take 15 to 20 seconds of your time. I've just cut short that time. I'll give you a minute to note this down. Then I shall move on to the next question. And I hope that you are able to solve it on your own. Have you noted it down, bacha? We'll do one more question and that would be it. One more question and I hope you can give me the answer to this one. This is question number 88 taken from your sheet. A liquid takes 5 minutes to cool from 80 to 30, 80 to 50. How much time will it take to cool from 60 to 30. The temperature of the surrounding is 20 degrees Celsius. I'll give you 2 minutes to solve this. So anyone got the answer for this? Okay. So how are we supposed to do this? The surrounding temperature is given as 20 degrees Celsius. 80 to 50, it goes in 5 minutes. So I make the first equation. I cut short the time. Theta 1 is 80, so it is 80. Theta 2 is 50. 80 minus 50 divided by 5. Do we understand this step? Can I have some reason that we understand this step? 80 minus 50 divided by 5, that must be equal to K into 80 plus 50. 80 plus 50 is 130. 130 divided by 2 is, okay, I write 130 divided by 2 minus 20. Do we understand this step? Yes or no? Then I make the step for this one. 60 minus 30 divided by T should be equal to K into 60 plus 30 is 90. 90 divided by 2 minus the surrounding temperature is 20 degrees Celsius. Now what I got to do is divide. This is my equation number 1. This is my equation number 2. I can divide 1 divided by 2. If I do 1 divided by 2, what do I have? 30 divided by 5 divided by 30 divided by T. 30 can get cancelled. Would be equal to 130 by 2 is 65. 65 minus 20 divided by 45 minus 20. So I will have T divided by 5 on the left hand side. that will be equal to 45 divided by, I think, 25. 1 5 goes, this is 5. So my answer would be 9. Do we understand this? Can I have some raise hand that we understand this? Well, if you can do this, it is absolutely brilliant. I hope that you have understood this. Can we move ahead? Before moving ahead, I'll just give you 2 minutes to note this down. Well done, everyone. I saw your answer on the screen. You could solve it. That is a present surprise. Good. And shall we move on to our next thing, which is the last subtopic of this topic? And it starts with this spectral energy distribution curve of black body radiation. It looks very tall. It's very simple. We have already seen this. Basically, it is telling us the emissive power or how much energy is emitted with different wavelengths, with different frequencies. Nothing more complicated about it. You must remember the name of this scientist. It was given by, practically it was given by Rumors and Prinsham. Mathematically it was explained by Planck. These are the two names that you must remember. So note down these names, and then we shall move on to the actual spectrum curves, and we will not be surprised to see the spectrum curves because we have already seen that curve. I have already told you the curve between E lambda and lambda. Do we remember that curve between E lambda and lambda, my dear friends? Our old friend Captain America is coming back after 70 years, and here it comes. After sleeping in ice for 70 years, in our case for 2 days, Monday, E lambda and lambda, the curve comes again, and you can see that curve on your screens right now. This is the curve between E lambda, which is the spectral emissive power. The spectral emissive power is nothing but your energy emitted per unit area per unit time of one particular wavelength. Do we remember this? Then we have drawn a graph between E lambda. As you can see, let me mark this. This is graph number 1, the upper wala graph. This is graph number 2, the thoda niche wala graph. This is graph number 3, the सबसे नीचे वाला graph. I have drawn a curve between E lambda and lambda. Do we see this? Can I have some raise hand that we see this? Yes, sir. It's a graph between E lambda and lambda. And as you can see, I told you when a body emits radiation, it will emit all types of radiation of all possible wavelengths. So from 0 till infinity, all sorts of wavelengths are there. Can you see this? Now these curves are drawn at different temperatures. Can you see the temperature? This is okay. I've named it ulta, so let me name them Sida. I just take this out and I will just call this curve as curve number 1, this curve as curve number 2, and this curve as curve number 3, so that everything remains looks similar. So these curves are now drawn at different temperatures, T1, T2, and T3. Do we see this? T1, T2, and T3. Now, my first question and the first thing that you will write would be this. If just looking at the curve and using some common sense, can you tell me which temperature would be more? T1. Now we are assuming that this is drawn for one particular body. This one particular body is emitting radiations at different temperatures. I have drawn that emission, that radiations at different temperatures, at temperature T1, temperature T2, and temperature T3 without telling you anything about that temperatures. Can you tell me which temperature do you think is more, T1 or T2 or T3? Which temperature do you think is more? I have not told you anything about it, but can you guess and tell me which temperature do you think is going to be the most bigger value, T1 or T2 or T3? And the answer is, which is the biggest temperature? I can't see your fingers, it's just too small, and today my this iPad has given me dhoka. It has no battery, so I'm using mobile, and in mobile it is very small and my eyesight is not good enough. Oh yeah, this is good. Yes, now I can see your fingers, and I think T3 is what you are saying. Yes, that is correct, beta. T3 is the highest temperature. T3 is the highest temperature, followed by T2 and followed by T1. So this is the first thing. This is the highest temperature. Now, what thing we can understand is, as you increase the temperature, mark my words, as you increase the temperature, the energy increases. Yes or no? Because energy is directly proportional to T raised to the power 4. More temperature will give you more radiations. Yes or no? That is one thing that we have understood, that more the temperature, the higher will be the curve, and that is what you will write. More the temperature, higher is the curve, because more is the energy. That is the first thing that we have noted. Now let us think about the second thing, and let us think about these lambdas. Now let us look at this lambda 3. This lambda 3 is the energy of the radiation, the wavelength of the radiation which has the most energy. Yes or no? Similarly, lambda 2 is the wavelength of the radiation which has the most energy at temperature T2. Lambda 1 is the wavelength of the radiation which has the most energy at temperature T1. Am I making it very complicated? It's very simple. Lambda 1, lambda 2, and lambda 3 are the wavelengths of the different radiations which have the most energy. Now, as you can see, when the temperature increases, the curve becomes ucha and ucha. But when the curves become higher and higher, the wavelength decreases. Can you see the decrease in wavelength here? Lambda 1, which is the lowest temperature, the wavelength is more. Lambda 3, where the temperature is highest, T3, lambda 3 is very less. So lambda 3, if I just write in terms of temperature, T1 is less than T2 is less than T3. Do we see this? But if I talk in terms of lambda, this lambda 1 is greater than lambda 2 is greater than lambda 3. Have you noted this thing down? You may not have to draw this diagram, but will take some time for you to draw this diagram in the sheet, in the notebook. So you draw a diagram on the sheet and just mark what I have written. T1 is greater than, T1 is smaller than T2 is smaller than T3, but lambda 1 is greater than lambda 2 is greater than lambda 3. This is the inference that you can draw from this graph. Am I clear? I'll give you a minute to note this down, then I'll shift to the next graph. Have you noted it down, bacha? Shall I move ahead? Okay, now move on to the second graph, and in the second graph, if you can see, similar graph, but instead of wavelength, I have drawn it frequency. Frequency F1, frequency F2, and frequency F3, and now everything reverses. What do you mean by everything reverses? Still, temperature T3 is more than T2 is more than 3.1. So you can see graph number 3 higher than graph number 2 than a graph number 1. Can I have some raise hand that this thing is similar? As temperature increases, the curve becomes higher and higher. Yes or no? But when instead of wavelength, I am drawing frequency and V is equal to F lambda, frequency and wavelength are inversely proportional. If you increase frequency, wavelength decreases. If you decrease frequency, wavelength decreases. Therefore, now in terms of frequency, frequency is F3 is more than F2 is more than F1. But if I talk in terms of wavelength, lambda 1 will be greater than lambda 2 will be greater than lambda 3. Do we understand this? Lambda standing for their wavelength, but see F standing for their frequencies. I'll give you just a minute. This is the same graph as graph number 1. The only thing it is frequency between frequency and energy. Do not forget that, because they might give you this graph and you might think that it is graph number 1 and mark that option. So please be careful. If you're not careful, you will lose marks. Shall we move on in life? Okay, moving on with life, we again come back to Avengers. Captain America has already come back. Who is going to come back is the Ant-Man, who has gone into this quantum realm, and he disappeared for some time. And all of a sudden in Endgame, was the movie of that? Yes, Endgame, he actually emerged from that quantum realm and came out and told them that time travel is possible. Spectral energy distribution is coming back. It is a graph between E lambda and lambda. Do you remember this graph between E lambda and lambda? We have already discussed that. Now we are talking about the area under this graph. What does the area under this graph give us? Do we remember that? The area under this graph will give us the total emissive power E. Yes or no? No or yes? Remember this? I'll give you a minute to note it down. I hope you have noted this down. Yes or no? Then from all these three graphs, what do we understand? That comes on the next slide, that this temperature T is inversely proportional to lambda. That means when you increase the temperature, lambda, which is the wavelength of radiation with maximum energy, decreases. Do we understand this? Point number one. Point number two, a very important point, the value of E lambda. Remember, E lambda, spectral emissive power, E lambda is proportional to T raised to the power 5. But if I make point number 4, the total emissive power is proportional to T raised to the power 4. Do we understand the difference between equation number 2 and equation number 4? In equation number 2, I am talking about spectral emissive power. In equation number 4, I am talking about total emissive power. Can I have some raised hand that we understand the difference? The area of E lambda D lambda graph or E lambda lambda graph will give us the total energy, total emissive power, which is equal to E times sigma T raised to the power 4. Their area A1 and A2, the area under this graph is proportional to T1 by T2 raised to the power 4. Do we understand all these points that I've highlighted? Everyone understands this. I hope no one is sleeping. We are all awake. This is only 10:30 in the morning. Yes. That's the speed I love. I'll give you a minute to note this down. We'll note some important points and we will note what this equation number 1 is known as. That is the last point of this chapter. I hope you have noted this down. Raise hand will give me more confidence. Not yet? Okay, I'll wait. Shall we move ahead? Okay, we move on to these golden key points. We have already discussed that. Just read it once. The curve drawn between the intensity of radiation and wavelength of frequency are known as spectral energy curve. This is a continuous emission. What do I mean by continuous emission? The curve is continuous. That means it emits radiations of all possible wavelength. It depends only on the absolute temperature. I have told you that as the wavelength increases, the energy first increases, then decreases. It becomes maximum. That maximum wavelength, when I increase temperature, the maximum wavelength decreases. Do we remember this? At a particular temperature, the area under this graph will give me the total emissive power E. Spectral emissive power is proportional to T raised to the power 4, but the total emissive power is proportional to spectral emissive power is proportional to T raised to the power 5. Total emissive power is proportional to T raised to the power 4. I'll just give you a minute to note these things down in the sheet. You may not write it, just note it down. We have already discussed them. Have you noted this down, bacha? Shall I move ahead? Okay. Then comes the last heading of this chapter, which is known as Vane's law or Vane's displacement law. Now, what is this Vane displacement law? We have seen that if I increase the temperature of this body, of any body, this body, if I increase the temperature of this body, it will emit more and more energy, more and more radiation. But I have seen that for one particular wavelength, it emits maximum energy. That particular wavelength E lambda is inversely proportional to temperature. Yes or no? When I increase the temperature, lambda decreases. Yes or no? That means lambda maximum multiplied by absolute temperature T is a constant. This constant is known as B. This B is known as Vane's constant, and lambda M is inversely proportional to T. This law is known as the Vane's displacement law. How do I state it? I state in this manner, and I hope you understand each and every word of it. The wavelength corresponding to maximum emission of radiation decrease with increasing temperature. Is every word of this definition clear to everyone? Please raise your hands if it is clear. Only one person is clear. What about the rest? Yes, we are clear. This is known as Vane's displacement law. If I talk about relation between frequency maximum and temperature, in graph number 2, we had seen that frequency is directly proportional to temperature, and this is how the equation will look like both for frequency and for temperature, and this is how the graph between frequency and temperature will look like. Do we understand this? Do we understand this? I'll give you a minute to note this down. Shall we move ahead now? Well, we move ahead with something known as Vane's fifth power law. And what is this Vane's fifth power law? We have already seen that the maximum energy, spectral emissive power, E lambda maximum is directly proportional to T raised to the power 5, but the total emissive power is proportional to T raised to the power 4. Do we remember this? Yes or no? No or yes? Please let me know. Yes or no? No or yes? I'll give you a minute to again note it down and the graph also. The graph is drawn between E lambda maximum now and T, not between E lambda and T. This E lambda maximum and T, E lambda maximum and T, and this graph looks like this. I'll give you a minute to note it down. Have you noted it down, everyone? Now, just to explain Vane's displacement law or the Vane's law, I would just want to give you an example. It basically tells us the lambda maximum is inversely proportional to temperature, and I will give you one practical example, and there could be questions coming on this, my dear friends. So please listen to it very, 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 very carefully. Vibgyor, do you know this Vibgyor? Do you know this Vibgyor? Yes or no? This red, oops. This red has the maximum wavelength, yes or no? Lambda is maximum. So if I talk in terms of lambda, lambda is increasing. This is lambda max and this is lambda min. Yes or no? Yes or no? Lambda min, lambda max. Now I will come on the big screen. Now, here is on the big screen. I'll just shut this window up now. Please listen to me very carefully and probably you will understand how you see Vane's law in your day-to-day life. Do I have your attention, everyone? Okay. Now, what does Prevost's theory of exchange tell us? This is one body, simple body. I am also a body. This is one body, simple body. Now, Prevost's theory tells us that this body is emitting radiations at all temperatures, and at the same time, it is also receiving radiations. Yes or no? Do we remember this? This is the summary of the entire chapter. This body is emitting radiations. Yes or no? Now the question is, if it is emitting radiations, why the hell I don't see them? I don't see those radiations coming out. Now, if you would have been born in my era, that was a good era to be born in 1979. I was around 15, 16 years old, somewhere around 89, 90, maybe 91, 92. There was a movie by the name of Predator. Have you seen that movie Predator? The original one with Arnold, where this alien comes and Arnold is caught in a jungle, and that alien kills everyone, and at the end Arnold obviously kills them. And even in your era, they created a movie, Alien versus Predator, Predator versus Alien, all that. Now, this alien or this Predator, which comes when he sees, and I remember very distinctly, he does not see human beings. He only sees their radiations. Now you have these infrared cameras. Have you seen these night vision cameras, night vision goggles? How do these night vision goggles work? Instead of actually looking at the body, we are actually looking at the radiations which are emitted by the body. You might have seen sometimes back, I was on some social media site and they were showing me how hot the ambience or atmosphere has become, and they were showing it by color codes. Color codes. Now, color codes. How does this color come with radiation? This body is emitting radiation, right? But we don't see them. Now, when do we start seeing them? Now, let us take the example of a copper block or an iron block. Have you ever seen in Discovery Channel when they show you red burning iron? Have you seen this red burning iron which is fluid in state? Have you seen that? Yes. Now, what happens if I have this body, and let us assume that this is iron or copper so that it does not melt. If I start heating this up, this will melt. Now, if this is iron or copper, and if I start heating it up, after some time, when it gets heated up enough, it will start to turn red. Yes or no? Why does it turn red? Why does it change its color? It is not actually changing its color. What is happening is when you increase the temperature of this body, it is emitting radiations. It is now starting to emit more radiations, but for one particular wavelength, it is emitting maximum radiations. And when that radiation come in your visible zone, and your visible zone starts from red, when this come in that visible zone, when it becomes so hot that it is emitting radiation which are coming in the red zone, then you start to see those radiation, and then you start to see becoming red hot. You might have heard this term red hot. You might have used it for different things, but red hot means it is so hot temperature wise that the emissions that it is emitting are in the red valley range. Do we understand this? Now, if I keep on heating it more, what will happen? It will emit more radiation, but the wavelength is going to come down. So after red hot, it will become orange hot. If I increase the temperature more, it will become yellow hot. It will become green hot. After that, it will become blue hot. It will become indigo hot. It will become violet hot. And if I increase the temperature more after violet, again, it will not become any hot because you will stop seeing its radiation. Do we understand this? Red hot, orange hot, blue hot. Now, you might have seen mother cooking, or sometimes you would have cooked Maggie. The flame of your burner is blue hot. Yes or no? You've seen this blue in color. Now, if you just for the sake of experimentation, if you just sprinkle 2 or 3 drops of water on that flame, and don't do that because you might get a chatka from there. But let's first say example for the sake of understanding. If I put 2 or 3 droplets of water on that flame, does it change color? Does the flame change color? Yes or no? Yes, the flame change color, and I've seen that change color from blue, it becomes orange, or sometimes it becomes red. Yes or no? Now, why does it change color from blue to red? It changes color from blue to red because when you are putting in water, the temperature falls down momentarily. And since the temperature falls down, the wavelength increases, and therefore from blue, it starts to appear red or orange or yellow. It's very hot right now. If you start, you can't look at the sun directly, but if you try to look at the sun directly, it will now appear more violet. Yes or no? It will now appear more violet. But when the sun is setting down and you are sitting on a seashore, on a beach, and which I've done many times in my life, when the sun is setting down, it's not violet anymore. It is more reddish and yellowish, and you start understanding how beautiful it looks. Why it has changed color? Because the temperature that you are receiving from it has gone down. Since the temperature has gone down, the wavelength has increased. Do we understand this Vane's law? So you see this Vane's law everywhere in your daily life. Do we understand this? So now, by looking at the color of the radiations, you can tell us, understand which is having a more temperature. A blue frame Is it having more temperature or a red flame? Which will give you more burns? The blue one will give you more burns because it is at a higher temperature. Do we understand this? Now, I have been a marine engineer and we used to have this gas cutting torch which we used to use in welding or for gas cutting. Now, it has this fancy knobs, oxygen, acetylene, all these knobs. And when you change all these knobs, the color of the flame changes. So once the color of the flame changes, you can understand that now you can use it for what further. Sometimes you will have to first heat up the object. So you make the color to orange or red so that you can heat it up. When you have to cut it, you use a higher temperature and your color of the flame becomes blue to violet to indigo. And that is how you cut it. You might have seen these gas cutters. They will look at the flame and tell you, okay, this flame can be used to cutting it. They know Vane's displacement law. They know that by looking at the color of the flame, you can tell us, can understand which is hotter and which is colder. This is Vane's displacement law, and this is my description to understand it in the simplest possible way. Is there any doubts? Do we understand this? Looking at the color of the flame, you can tell what the temperature is. Yes or no? Okay, so we move ahead in life. We always have to move ahead in life because life cannot become stagnant. Life cannot become stagnant, and here we go on to the last part of today's class, and which would be which would be what I'm doing here. I'm doing all sorts of stupid things, but this is what I want to tell you. Applications of Vane's law to compare the temperature of given stars, observing their color, because color of a star identifies its temperature. If I see a blue star, a white star, and a red star, looking at the color of the star, I could tell you what the temperature of that star is all about. Do we understand this? Can I have some raise hand that we can use this Vane's law in finding out the temperature of a body by looking at its color? I'll give you a minute to note this down. Have you noted it down, bacha? Yes or no? No or yes? Okay. Then move on to the last heading of this chapter. We'll be solving the question in the next class. Solar constant. And what is the solar constant? Sun, the ultimate source of energy for us, clean energy, solar energy, nuclear fusion. Two smaller atoms, two smaller nuclei become a heavier nucleus. Sun is radiating energy in all possible directions. Dung, 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 dung. This is my sun. I mean, your sun, our sun, everyone's sun. This is emitting radiations. The radius of sun is r. Do we see the radius of the sun r? Then d is the distance between the sun and our mother planet Earth. Do we see this? The sun is emitting any energy. How much energy we are receiving per unit area, per unit time is known as the solar constant. How much energy Earth is receiving per unit area, per unit time, that is the solar constant. We are receiving 1340 watts per meter square. That is free energy. Free energy. Sun is giving us free energy. You don't need cars. You don't need planes. Sun is giving you energy. Use it. Use it in solar cells, solar panels. And this is going to be the future of energy, if at all there is any future. 1340 watts per meter square. That is the energy we receive. How much of this we can use? This is clean fuel, clean. No emissions, no carbon dust, nothing. No radioactive material. Pure energy. Solar constant. Do we understand this? Do we understand this? And the formula for this is derived from here. The formula for this is E into R square by D square. This is known as the solar constant. E is the emissive power of sun. R is the radius of sun. D is the distance between the sun and the mother planet Earth. You will have to remember these relations and the value of this solar constant. Can I trust you on that? Can you remember this? Raise of hands will give me more confidence that I can trust you. I'll give you a minute. Note this down. I hope you have noted down the value of solar constant. I have also hope that you have noted down the formula E into R square by D square. Then comes another set of formula again for the solar constant. The solar constant S is E into R square by D square. Have you noted this formula? Now this E is the emissive power of sun, so it is sigma. We are taking sun as black body. Sigma into T raised to the power 4. So this becomes another formula for solar constant. From here, you can find out the temperature of sun. Yes, you can find out the temperature of sun using this. You can find out the temperature of any star using this if you know the radius of the star and you know the distance between the star and us. And you know the solar constant. Okay. The value of the solar constant is 1340 or 1.4 kilowatt per meter square or 1.94 calorie per minute or 2 calorie per minute per centimeter square. So note this down. All these formulas, any one formula can come. Well, I hope you have noted down this formula for solar constant. It's already there in your sheet. Just remember these formulae. What we have discussed in today's class. In today's class, we started with Stephen's law and we saw that Newton's laws of cooling is nothing but derived from Stephen's law. The rate of cooling is directly proportional to the difference in temperature. Then we saw another form of Newton's law where instead of theta, we are using theta 1 plus theta 2 by 2. We saw how we can solve questions based on Newton's law. Then we moved on to Vane displacement law. We saw that if the temperature increases, more energy is emitted, but the wavelength decreases. Red hot and violet hot. We have understood the difference between blue flame and red flame. Lambda maximum is inversely proportional to temperature. We have seen Vane displacement law. We have seen how looking at the temperature of a flame, we can tell the temperature. We can tell the how looking at the color of the flame, we can tell the temperature of the flame. How looking at the amount of energy we have received from sun, which is solar constant, how we can find out the temperature of the sun. I hope you remember all these formulas. In the next class, we'll be doing some questions on this. We'll moving on to the next topic, which I think is optics. We'll move on to optics from the next class. We'll also solve some questions. in the next class based on this, based on the entire chapter. For that matter, we'll be solving a lot of questions. Please come prepared in the next class, and I'll see you there. Till then, take care. Have a nice day. Stay home. Stay safe. Bye bye.